So it's my pleasure to introduce Steve Koonin from CUSP to kick us off for the morning with urban data and decisions.
Good, thank you. About 12 years ago, when I was working for BP, the oil company, I had the idea that the intersection of energy and modern biology was going to be particularly interesting and fertile, and convinced BP to put in $500 million, some fraction of which was spent here at Berkeley. In fact, in this building where the Energy Biosciences Institute lived for 5 years from 2008 to 2012. You can read that on the posters outside. About 6 years ago, when I was finishing up a stint in the Department of Energy in the government, I thought that cities and data was going to be particularly interesting, and so went to NYU to start an enterprise called the Center for Urban Science and Progress, which explores that intersection. When you think about it, cities seemed at the time, and I think still are, a pretty powerful venue for data science. Cities matter. Most of the world lives in cities now, and that fraction is growing with time. The data are plentiful and diverse. We have the digitization and opening up of government records in cities around the world, and we have proliferation of sensors everywhere in cities. And there are things to do. There are technologies and methodologies to develop that let us acquire, integrate, and analyze data. There's a science to understand about cities, both their behavior of a given city over time, as well as the intercomparison of different cities. And then there are innumerable applications for government and the private sector. And so just about 6 years ago, there was an announcement. There's the mayor. I was standing in the back over there because I had no idea what we were actually going to do. And now 6 years later, there is a story to tell about some of the projects we've been working on and some of the things we've accomplished. So I came out of the Department of Energy in 2011 with sort of the way a physicist would say it. I was going to go instrument a city. I was going to try to understand about the condition and operation of the infrastructure. I was going to understand about the environment, and I was going to understand about the people and how they all interacted with one another. And there is, of course, lots of data out there. Some of the challenges are, can you get at the data? We've got organic data flows, the kind of data that the city generates just in the course of its operations. Administrative records, parking permits, census, things of that sort. There's transactional data, sales, communications. There's all kinds of operational data about how the traffic is flowing or the utilities are running. And then we've got, of course, social media. Sensors. We all carry sensors in our pocket these days. There are portal sensors, traffic sensors. And then there are novel technologies, some of which I will show you, that let us get unusual data about how the city is operating. So when we started up the center, there is a research strategy that we laid down, actually pretty consciously at the beginning. We were going to focus on the data. I was not interested in, say, a new way of integrating photovoltaics into a building or new technologies for concrete as much as they might be important in making cities better. I was going to focus on New York City because that's where we were. We're a unit within New York University. But also because the more data you can have about the more variety of data you can have about a given city, the more possibilities you have for linking data sets together and getting a more interesting understanding. Having traffic and health and pollution, say, in New York City is much more interesting than having traffic in 10 different cities around the world. Also, we have to work closely with city governments, and it is hard enough to work with one city government. The thought of working with a dozen at once is just daunting. We wanted also to establish a center that owned the data, that it would be intimately familiar with it. It would have differential access, select access, if you like, to certain data sets and be able to deploy unique sensor systems. And then to create, having grown up in a part of my life with the national laboratories in the US, I knew that facilities are important ways of generating data, of nucleating researchers together. And so the research structure is a set of user facilities, which I'll describe a little bit about each one of them, a data facility, quantified community, and an urban observatory, which I'll describe a bit more in detail. A set of themes, building informatics, can we understand about the buildings, mobility, obviously, sounds, energy, and then a whole host of small projects that get executed, some in collaboration with companies, others in collaboration with the government. There are a set of themes. I'm not going to go through them in detail, but energy in the built environment, social services delivery, very important in a city like New York, mobility, obviously, event and pattern detection are important. We'll see that the city is a recurring entity. Every day looks more or less the same as every other, and so identifying norms and anomalies in those patterns is really important. Environment and air quality, and then a set of projects for the agencies. Fundamentally, this kind of work, at least in its applications, there are only about 3 or 4 real applications of big data for cities. One is resource allocation. Can I figure out how to efficiently allocate resources, whether it's police on patrol or trash pickups, or where do I put pre-K facilities? The second is anomaly detection. Can I find, we heard yesterday in some of the network talks about detecting anomalies. Well, there are anomalies in cities that can be detected using the data. And then the third, I think, is to construct and validate predictive models for the city. You need the data in order to be able to do that. And all of these things fall more or less in those 3 buckets. So let me start with some of the records data. New York City is a big, talent-rich, data-rich entity. It's got, I don't know, 24 departments, and Bloomberg, in the last several years of his last administration, took the initiative to aggregate all of the data feeds around the city into something called DataBridge. This is a now quite old picture, but you see it's got feeds from sanitation, from finance, from transportation, and so on. These data sets, of which there are many, only about 1,200 open to the public, are what you would call a dog's breakfast of data. It's really a data heap rather than a data facility. And there are various entities, some in the government, some outside, who are trying to do interesting things by correlating and analyzing these data sets. The federal data are also available. This is a map from the Census Bureau of the Gini index across New York City. It's a measure of income inequality. Never mind the details, but I put it up just to show you the granularity with which the demographic landscape is known and is available. So one of the facilities that we're building is the Data Hub, which is, let's go back, a set of multi-level access data sets that have been curated to allow coordination and linkage, a set of tools that let ordinary mortals like social science researchers get at the data. Julia Lane, who is the vision and brains behind the data set, has developed or is developing, together with some of the folks in Chicago, a kind of recommender system for data sets where you might look at a data set and then get suggestions about other data sets that you might look at. Very interesting for a social science researcher. This facility is up on the web and available. I think you need to sign up and get approval, but it's there and operating. A second facility we have built is what we call Quantified Community. It is a way of doing intense instrumentation of a neighborhood of, let's say, 10,000 people or a big building to understand, again, infrastructure, people, environment. It's instantiated in Lower Manhattan in a neighborhood called Greenpoint in Brooklyn. We use a combination of records data and in situ sensors to try to get at what's going on. Here's an example. This is 1 month of hits on a Wi-Fi access network in Lower Manhattan. And of course, your phone, if the Wi-Fi is turned on, pings or gets pinged by the access points as you pass by. And this is, as I said, about 30 days, July 2015. And what's separated out are the passers-by, the visitors, and the folks who actually connect. And you can see several things. One is, again, the repeating pattern. Pulses, actually 3 peaks every workday, in the morning, at lunchtime, and in the evening. You can see the July 4th holiday, which showed up over here. And by looking at when you ping certain handsets, you can determine who lives in the area, who works in the area, and who is just passing through. We do a lot with street-level imaging. There are 600 traffic cameras in New York City. The feeds are available publicly, I think once every 10 seconds or something like that. Some of the scenes have Abbey Road-like scenes where you have a zebra crossing or a crosswalk that's visible. Some of our folks, Greg Dobler and collaborators, developed a neural net that really just lets you count the number of pedestrians in a crosswalk. And it's not perfect, probably only about 60% efficient, but nevertheless useful to get time dependence. Here is an example. Going vertically is just traffic camera number, and it's a heat map of pedestrian counts. Again, you can see morning, lunchtime, and evening, and you can see differences on the weekends compared to the weekdays. Typical pulse shown over there, and again, you see anomalies when there are holidays. You can also segregate out neighborhood character. Greenwich Village looks very different than Midtown Manhattan, for example. So this is an example of a very large found or serendipitous data set that you can use to start to characterize what goes on in a city. Use cases for this stuff: what good is it? Lots of things: air quality, sewer overflow, et cetera, et cetera. I'm not going to go into many of the details. The charts are there, and you can look at them at your leisure. Let me move on to sensor-based data. One of the projects we started early on was sound in New York City, or we called it noise at the time, actually. I grew up in New York City. I left 50 years ago and only came back about 6 years ago. The city is wonderful, but in fact, the biggest quality of life issue, at least for me, was the noise. The guys bang the trash cans at 2 in the morning every night. It makes it really difficult to sleep. And so I swore we were going to get those folks. We started up, we hired a couple of postdocs about 5 years ago. Faculty member Juan Bello, who's a music guy, actually, he's a music technologist, came in, and the project has since taken off. There's good NSF funding, good collaboration with the city. The 2 postdocs, Charlie Midlaws in particular, designed a box which is about $85 when fabricated by the hundreds in China. It exfiltrates the data through local Wi-Fi, and the innovation, there's several innovations, but one of them, it's got a MEMS microphone, which is good to plus or minus 2 dB, which is what you need to enforce the noise code in New York City, is a 2 dB precision. Here's a picture of one of them deployed near NYU. You can see the windsock that covers the microphone, the wire that does power and data. And of course, you don't think of everything, and so you realize you need pigeon spikes at some point to keep the pigeons off. We've now got roughly 50 nodes deployed around Washington Square and some in Brooklyn as well. We'll have 100 by the middle of the year. They're taking sound data 24/7, sound pressure level, so not the sound itself, but just the dB level. And they're taking random samples of audio snippets at 15-second lengths at random. Why is that? Well, and of course, it's all real-time telemetered back. Why 15-second samples? You are legally not allowed to record sound in New York City on the street unless you are present. And so having a microphone there just to record voices. This is a wiretapping law, basically. It is not legal. We thought about sitting a graduate student at the base of each microphone, but that's not very efficient. So the lawyers, in the end, said 15 seconds of audio is good enough. You can do that. And that's used to train up an algorithm that does feature detection on the sound. It's done, ultimately, it'll be done in the box. And so no sound is ever actually recorded. It's just feature extraction. So I think if the sound is working, we can do a demo of the algorithm. Let's see if that works. When the horn blares, the horn is there. The drill shows up and so on. Basically, it converts the audio stream into a photogram, a two-dimensional frequency time plot, and then does image recognition on the frequency time plot. Okay. So this is done in collaboration with the City Department of Environmental Protection, who are responsible for enforcing the noise code. All right, let me turn to a different way of looking at the city, again with sensors. And the story here starts back just about 7 years ago. Well, no, 6 years ago. When I saw that picture in National Geographic, it's a thermal infrared image of lower Manhattan. And so we're looking at heat, not light. And there are lots of interesting things when you study that image. The first is you can read the thermostat of every apartment in that building. Some are hot and some are cold, all right? The second is that building, we have correlative data about it. We know what building it is. It's that address. It's got a data center in it. And so it's hot on the bottom and hot at the vents on the top and cool otherwise. And you can look at those buildings and be horrified. This is a city public housing project, and the thermostats are turned on, the heat's turned on, and people have the windows open to keep the apartments cool. All right, so terrible. NYU buildings are the same, but that's a different story. So when you think about this for a minute, it's pretty interesting. It's a single sensor. It's this one infrared camera, not an ordinary camera, but nevertheless a single sensor. It's synoptic. There are hundreds of buildings in the scene here at once, so you get broad coverage. It's non-permissive. I didn't need to get anybody's permission to figure out what the thermostat settings are in those apartments. I just look. All right? It's persistent. It's not like a drone or an airplane or a satellite where you get one picture every couple days if you're lucky from the satellite, or the airplane similarly has got to fly over many times. And it's got high granularity. You can see down to the level of individual offices or building units. And so that seemed to me pretty interesting. I brought into CUSP 2 astronomers who were getting tired of doing cosmology and wanted to do something a little more interesting. And so we have now done a variety of imaging modalities demonstrating what it is one can learn about the city in the visible, in the infrared, hyperspectral, and hypertemporal, and I will explain those last few if you don't know what they are. About 3 months ago, CUSP moved into new offices, but in our old offices, where we were for 5 years, this was one of the views. It's a view looking up the east side of Manhattan. North, you can see the Empire State Building in the upper left. That's about 3.8 miles away. And there are about, I don't know, I think there are about 1,000 buildings in this scene. The lower part is residential, and the upper part is mixed commercial and residential. And so we've done a lot of different things just by watching. I'll show you examples of some of them. Detection of aerosol plumes, urban vegetation, hypertemporal imaging to understand the electrical grid, and so on. And I'll take you through some of that. First, you got to know what you're looking at. We have a 1-foot resolution LiDAR scan of the city. It was done about 6 years ago, still good enough. And it gives you the topography of the city at 1 foot resolution, vertically and horizontally. And it's a simple exercise in geometry. It was actually done by a Yale undergrad to take that data set together with the image and identify the X, Y, Z coordinate of every pixel in the image. Then you can drop down to the XY plane, tap into the city records that tell you what the building is, what goes on there, how big it is, what its heating system is, and so on. Right? So we know what we're looking at. This is a segmentation of that same scene, fusing together the image, the LiDAR map, as I mentioned, the city data, which is called Pluto, which is all about the buildings, and energy benchmarks. The buildings have been coded according to their energy use intensity. The hot ones, the red ones, turn out to be hospitals and recording studio or broadcast studios, which are, of course, running 24/7, so they use a lot of energy. And then the rest, as shown. Also, we have outlined in black those buildings that heat by heavy heating oil as opposed to natural gas. You'll see in a moment that that's an important source of pollution in New York City. So this is a time lapse of the lights in the visible over one night. There are about, I think there are about 20,000 lights visible there. And you can see the Empire State Building just went off. We go through the night. Some of the residential goes on and off. They change color. And then we go through the daytime. Sun comes up, starts moving across the sky. Clouds will drift by in a moment. And so the question is, we have hundreds of terabytes of this stuff. What can you learn by analyzing these images? So the first thing we did was to start to look at individual lights or windows. We went through the IRB, the Human Subjects Board at NYU, and said we want to look at windows, and they said, what do you mean? You can't do that. And we said we will keep the resolution low enough so that you can't tell what's going on in the window. We will do all the analysis aggregated and anonymized so we don't know what we're looking at. And oh, by the way, everybody else looks in everybody's window anyway in New York City. New York City has the highest per capita sales of binoculars and telescopes in the world. So, all right. Greg Dobler, this was early days, about 4 years ago, by hand segmented out the image into 4,000 sources, lights. And this is one night in one source. I have no idea which. It doesn't matter. You run a change detection or change point detection algorithm, as we heard a little bit about yesterday. And you can see that the lights start out at 7 o'clock at night, goes down a little bit at 9 o'clock. It's interesting that the transitions occur mostly on the hour. At 23:30, there's a big drop. It looks like somebody went to bed. And then a bit of brightness along about midnight, 12:30. Baby woke up, insomnia, who knows what happened, all right? All right. So you can categorize all of these on-off transitions. Yeah?
One window? Or?
Yes. This is one window for one night. Okay. We identify what we call a big off transition when it looks like people went to bed. And we have a big on transition as well. This is a catalog or a graph over 3 weeks of big offs on the top and big ons on the bottom. And you can see, again, this kind of periodic pattern, weekends different than weekdays and so on. And sometimes, because this is just like real astronomy, you get data drops when the system wasn't working at all. And so we've gotten much better now. This was about 4 years ago. Interestingly, the lights correlate very well with power usage. We could go to Con Ed and get the power consumption for the buildings that are in view. And it correlates pretty well with that. So this is a way of doing, if you like, remote metering of the buildings, at least in aggregate. Sleep-wake rhythms were interesting also. If you take 2,000 residential windows and look on a typical Monday and just plot in order when did the lights go off, when does it look like they went to bed, you get this kind of graph. So that's the natural order of the windows on a Monday. And then you go to Tuesday and plot the same windows in the same order, and you see that the pattern gets rattier. But if you replot the Tuesday windows in their natural order, it looks a lot like the Monday windows. And so at the micro level, people are kind of random when they shut their lights out, but at the aggregate level, it's pretty darn repeatable. And we were interested to get validation of that by looking at some Jawbone data. Jawbone, the motion detector, published some data about when people go to sleep in New York City, which is the blue line, and our big offs are not bad. They go to sleep a little bit later in our data than the Jawbone. Our data are for Manhattan. Jawbone is for all of New York City. The suburbs sleep a little bit earlier than the young people in Manhattan, so it's probably okay. But anyway, you get a sense of this. You can start to correlate with health, with noise, and so on. All right. One of the surprises was our ability to detect soot plumes. I show you about a 2-minute loop during the daytime on the top of our standard view. And on the bottom, I show you the subtracted image where we've taken out the background. And you can see this big white blob that comes out there as it runs in the loop. And that is that. It's not the same source, but this is an example of it. It is the biggest source of particulate pollution in New York City. And being able to identify who's doing it, when, where is the stuff going is really important. So we've got now an effort to really do the image recognition right. It's not so easy to recognize these plumes against the heterogeneous background of the city automatically. But it's in process. There's money we've gotten to do that. Another way of looking at the city is hyperspectral. Your camera takes an image in 3 colors, RGB. You can spend $70,000 and buy a very fancy camera that takes a picture in 800 and something colors. Namely, it produces a spectrum for each pixel, so you've got a data cube. And by looking at the spectrum of each source, you can type it. So here, for example, are laboratory spectra of different lighting sources, LEDs, high-pressure sodium, and so on. And so you can take this kind of broad picture of the city, and you can assign a technology to each of the lights that you see. Here's a blow-up of the Manhattan Bridge, which is over here, and you can see that the necklace lights are LEDs and the roadway lights are high-pressure sodiums. Why is that interesting? Well, you might want to know when you look at the residential buildings who's using efficient lighting and who isn't, if you're in the market of trying to either improve the efficiency because you're a utility or you want to sell people light bulbs. But also there's a science thing to understand here called the rebound effect. Namely, if I give you a more efficient light, you might be tempted to leave it on longer and thereby partially negate the efficiency savings. It's called rebound. Jevons discovered it in the 1850s or so. So we have a natural way of studying rebound. You can see when people switch technologies, did they keep their lights on more after the switch? I think, let's see, okay, we're doing okay on time. Hypertemporal imaging is another one that we have demonstrated and now have money from ARPA-E to explore on grid dynamics. Almost all of the light sources that you see in a city flicker at 120 hertz. So that's just twice the line frequency because the brightness is the square of the voltage. If you have an incandescent bulb, you can see it quite easily. When sources turn on and off in your apartment, for example, you will see a drop in the brightness or a glitch in the flickering because of the load has changed as your fridge turns on and so on. And so you can look at that 120 hertz by putting a shutter in front of the camera, driving it at 119.75, beating down the 120 hertz down to a quarter hertz for second period, and then imaging those much more slowly changing scenes. This is a loop in which we did that. We image at a quarter second, so 4 hertz, and so 16 images per cycle. If you look at that one source, this looks like real astronomy. I mean, that's what it looks like. And then you can segment out the time dependence of that source and do the Fourier transform periodogram and see that it flickers at about the right period. Why is that interesting? Because we can not only measure the frequency, which is not so exciting, but you can measure the phase. And you can see the phase change with time as different loads come on, as different generators come on and off, and so on. So this change in phase across the whole city in real time is something that we can do. Thermal is also real interesting. I'll show you 2 thermal infrared images, actually, yes, taken about 2 minutes apart. This is the west side of Manhattan, Empire State Building about 2-point-something miles away. And you can look at the difference. And, okay, you see some people burning hot stuff over here. But you also see that, which turned out to be really pretty interesting, what's going on there. So we have building ID. We identify it as a building not far from Google in Manhattan. And what's interesting about that image is you see the cooling towers on the top. So we caught one of the cooling towers turn on. That's pretty interesting because I've now got a way of watching the HVAC systems over many hundreds of buildings at once operate, turn on and off, and get a sense of energy use, occupancy, and so on. Just to demonstrate that, the persistence of that, this is one building vent taken in the infrared at about a distance of 400 meters over the course of a night. This is 10 at night to, 8 at night to 6 in the morning. And the blue is a set of pixels off the building vent. The red is a set of pixels on the building vent. And you can see the heating system of the building turning on and off. And again, the ability to do this for hundreds of buildings at once, do pattern identification, outliers, and so on, we think is pretty interesting. All right, I think this is the last imaging one. We can do hyperspectral in the infrared. So this is from 7 to 13 microns, not visible, which is like a half a micron, 7 to 13, long wave infrared, 128 colors over that spectral band, and each simple molecule has a different spectral pattern. And so you can see chemicals getting emitted from the city in real time, broad coverage. This is a set of images taken from Hoboken, and you very clearly identify Freon 22, which is an ozone eater, and it's coming from old refrigerators. All right, not so interesting perhaps. This one was more interesting. We found acetone on afternoons. There it is in the image. Let's see, play the movie. This is about 3 hours or so. You can quite clearly see the acetone. This instrument is remarkably sensitive. We sent some graduate students out with cans of dust-off, which is some organic molecule, at about 2 miles, and they let the cans off, and you can see them very easily. So acetone, we said, aha, nail salon, right? Not really. We did building ID, of course. We identified a 677 Washington Street, which is there in Manhattan. It turns out at 679 is Couture Cleaners. And they have on-site dry cleaning, and so we basically saw them doing their business every day and can get a sense, again, of how much every day goes on. All right, I'd like to leave some time for questions. One other sensing thing and then one other model thing, and I think we're about done. On last Saturday, the 16th of March, would have been St. Patrick's, was St. Patrick's Day. We were supposed to have a LiDAR overflight of 2 square miles of Brooklyn. It's unbelievably complicated to get a plane to fly in New York City legally. but it would have carried a very sensitive hyperspectral imager and a very fancy LiDAR system to be able to do LiDAR with 5 centimeter resolution, which would have let us identify curbs in the street and so on. Unfortunately, the LiDAR instrument got sick and they had to send it back to Florida, so we'll get to do this overflight in another week or two. But, you know, that kind of high-resolution geometry of the city is of interest to many people, particularly when you combine it with hyperspectral imaging so that you get a sense of what the material is at the same time as the geometry. And then I think this is the last research thing I have. We brought to CUSP about 2 years ago Paul Torrens, who is a geographer from Maryland, and you know, I used to think geography was the most boring subject ever when I was in elementary school or middle school. It turns out it's really interesting. Paul is a GIS expert, but more interestingly, he does modeling of the way people interact with infrastructure, and in particular, crowd behavior. So let me play this video. This is an earthquake. So there's physics in the way the building falls, and then the crowd reacts to the earthquake. These are independent agents. Each agent has a mental state, perception, and has body motion that's been captured in a motion capture suite. So they're meant to be as realistic as possible about how people move in crowds, particularly in response to evacuation situations. I keep asking him, how do you know how accurate this is? What are the measures? He says, we're working on it. But it makes for pretty good pictures. And, all right. Let me close a couple words about education, because it's important also to our research program. We're now in our 5th cohort of a 1-year master's program in urban informatics. The students come from a tremendous variety of backgrounds, everything from data science to economics, cognitive science, physics, civil engineering, urban planning, economics, and so on. They get about 30% of their curriculum in data science, not at a very high level, but enough to be able to solve problems with large data sets. About 30% in urban, how do cities work, what are the problems, and then about 40% in a capstone project. Lots of students, our average class is now running about 70, and they go off and find wonderful jobs everywhere. But what I wanted to put up was lots of projects. We'll have done about 50 projects for the city by the end of this year. Everything from data poverty to understanding neighborhood dynamics to the condition of New York City parks. How do people use parks? What's the economic value of a park? And so on. Again, up on the web, you can find these projects. Let me just close with a couple of problems that we've got as we do this, and other people do this in other cities around the US and around the world. We don't have a good way of describing cities. We need an ontology. It's not well defined. Data standards are terrible. Data hoarding is a big problem. I like to say hoarding of data is the second most basic human urge. The academics do it because of priority. The private sector does it because of its commercial value. And the government departments do it because they don't want to be embarrassed and because it's turf. In terms of the real applications, we haven't quite figured out yet who the customers are in this. It's not obvious how to make money doing this, which is probably important if it's going to be sustainable. Citizen acceptance, privacy, control, who gets to use the data. I mean, this chart is probably a year or more old, but it's been brought to the fore with the Facebook story in the last week or so. I think there's a big discussion to be had about who owns the data and what can you do with it. Thank you. Let's start in the back. You were first. Yeah?
Are there any initiatives specifically for extreme events like disasters or hurricanes?
Yeah. So there are lots of people who try to do this kind of thing for resilience issues. We did, I mean, there are many people who do it. I'll just give you one project. We did we were interested in the economic impact of what happens if you knock out a subway stop. So rerouting of people, lost time and so on, and then not only one, but 2 subway stops. If I take out 2 simultaneously, how much impact is there on different pairs and so on? But there's all kinds of things about flooding and others. So yeah, that's certainly one application of this kind of thing. Yeah?
Could you use this hyperspectral imaging to detect illicit drug activity?
Absolutely. We were, when we started, we were looking from Hoboken out to the west side of Manhattan. I was hoping we'd find a drug lab, but it's the wrong neighborhood to be looking, right? So we have a grant into NSF. I don't know if it's going to get funded. So a little bit about the instrument, okay? So the instrument is a $2 million instrument. We could not buy it, but I was able to get money to rent it for 2 weeks. And we had a crew come with the instrument from the manufacturer, the owner, Aerospace. And so we took this data set. We have a proposal in to NSF to buy a slightly less capable instrument for about $1 million, $1.5 million. The instrument, because it's infrared, has to be cooled. And so it comes with a big dewar of liquid helium. And the reason we were looking from Hoboken rather than our headquarters in Brooklyn is because we could not get the dewar of helium up the stairs to the roof. It just wouldn't fit. So we went to Hoboken. The one we're trying to buy has got a Peltier cooler, which is a solid-state thermo cooler, and so it basically is portable and handheld and so on. But we think there's a lot of potential to just drive around the city and look and say, what's that thing coming out, right? Yeah. It's got all kinds of interesting legal issues, too, if you want to use it. You know, I can't remember the name of the court case, but the cops in, I think, Marin County or Sonoma were finding somebody growing marijuana some years ago by infrared imaging, and it was ruled illegal search and seizure. It's not my business. I just demonstrate capabilities, right? Yeah.
So with regard to the last slide you had and the customers, I'm wondering, it seems like you have a ton of really interesting data, but with respect to what you described now, you were really just outlining the data more than problems that could be solved using the data. Is CUSP also looking into like the problems in cities that can be solved using data?
Yeah, yeah.
One in the center I saw, improving NYPD's crime pattern detection. That seems to be actually operational as like.
Right. So look, there's mobility, there's resource allocation, safety and security. One of the things we did, which is not rocket science, but gives you a sense, New York City has an open data portal, or not an open data portal, it does have that, but it has a portal for services. So if I need shelter, food, and so on. And some of the students several years ago analyzed who was using that portal and discovered that there were 2 neighborhoods that were not using the portal as much as they should have been given their demographics. And so the city started an advertising campaign to boost the use of that and access to city services. So that's kind of one simple problem. Some of this is not, fancy rocket science. It's just applying standard data science to a problem. Another one we've gotten started is smart shelters. So who's using the homeless shelters? What are the return rates? And that sort of thing, and how can you make it more efficient? So there are lots of problems that we are working on and other people are working on. Yeah. All right, yeah.
It seems like one of the strengths is that you have access to a lot of different data streams. Most of the use cases you showed so far sort of making use of single, like a single imaging facility or whatever.
Yep.
What are the synergies you can get between all these different sources?
Yeah, so I'll put back up this picture just to remind you. Why didn't I show this one? Just by the way, that's the footprint of the buildings that you see in the scene. But that one is a fusion of 5 different data sets, right? So I know the detailed building characteristics, I know the image, and I have the time-dependent video, the LiDAR, and so on. So that's a start at that. But we've not done, frankly, a tremendous amount of, let's say, correlating sound together with when the lights go on to get us, and public health issues altogether. I mean, that's all territory to be explored, but not yet. Yeah.
Is privacy dead?
I think so. I think so. There are just so many, the digital exhaust, the closed-circuit TV, the imaging, the cell phone tracking that is certainly possible, not only by the phone company, but by other people with some modest technical skills. I think privacy is dead. But
it's like putting a hole in the dike.
Yeah, I think so. I mean, we're an academic organization. We don't have great resources. We can already do things that we don't. I mean, I should say, we don't. No, really. We have a chief data officer, Julia Lane. All of the students get trained in data ethics, data privacy. All of the things we do that touch on people go through the IRB, and we carefully log access to restricted data sets and so on. So we're trying, all right? But as you all probably know, if you're inside one of the big companies, there are no such restrictions as far as I know. So you get things like, yeah, privacy's dead. So, yeah.
So
Steve, yeah.
it's pretty amazing you can get such a high resolution, real time, and very detailed measurements of, say, frequency and phase. Yeah. Is it possible to also get voltage measurements? Because with the 3, then you know everything about the net.
Yeah, I think, so to get the voltage, you need the brightness, but I mean, you need the brightness, basically, for an incandescent bulb. I don't know what happens with fluorescents or LEDs. And that's going to be pretty hard because of the turbulence in the atmosphere, right? You see all kinds of changes just from the seeing the turbulence. So I don't believe so, but I don't know. I mean, what you saw with the hypertemporal, the grid imaging, was taken with a pretty small lens. We've gotten money from ARPA-E, and the project has just actually bought a bigger lens and a video camera. The postdoc shows up in a week, and we'll see just how far it can be pushed. Yeah, the data, right. Access to the data is everything. That's why a lot of CUSP is about getting new data sources with the sensors, right? Okay. All right. Okay, good, thank you.
Refreshments outside, and we resume at 10:45.